Hello and welcome to Fun Facts Online. Today we are turning our eyes upward, away from the screens in front of us, and toward the oldest frontier humanity has ever known, the night sky. If you were to stand in a dark open field tonight, far away from the city lights, and look up, your eyes might still trace the ancient patterns of Orion or the Great Bear. These constellations have guided sailors, inspired myths, and served as our calendar for thousands of years. But if you wait long enough in that dark field, looking up at the zenith, you will see something that your ancestors never did. You will see a silent, steady point of light, moving in a straight line, defying the rotation of the stars. Then you will see another, and then perhaps a whole train of them, marching across the sky like pearls on a string. These are not meteors, and they are not alien visitors. They are the new architects of our orbital environment. They are mega-constellations of satellites designed to beam high-speed internet to every corner of the globe. While they promise a revolution in connectivity, they have sparked an unprecedented conflict that pits the future of global telecommunications against the oldest of human sciences, astronomy. This is the story of the crowded sky. It is a crisis of light, data, and debris that threatens to close our window to the universe forever. To understand how we got here, we have to look at the history of the space race. For over half a century, space was the exclusive domain of governments. Satellites were large, expensive, and relatively few in number. As recently as 2010, there were only about 1,000 active satellites orbiting Earth. They were invisible to the naked eye, silently handling our GPS, our weather forecasting, and military communications. But then came the private space revolution. Driven by reusable rockets and the miniaturization of electronics, companies like SpaceX, OneWeb, Amazon with Project Kuiper, and AST SpaceMobile began a race to colonize low Earth orbit, or LEO. Their goal was noble in principle: to provide low-latency, high-speed internet to the 3 billion people on Earth who currently lack reliable access. But to do this requires physics that dictates a completely new approach to space infrastructure. See, old-school communications satellites sit in geostationary orbit, or GEO, which is about 35,000 kilometers away from Earth. That distance is great for coverage, but it creates a time lag, known as latency. That lag is why satellite internet used to be terrible for video calls or gaming. To eliminate that lag, the new generation of satellites must orbit much closer, between 300 and 1,200 kilometers. But there is a catch. At that low altitude, a single satellite can only see a small patch of Earth at any given moment. Therefore, to cover the whole planet continuously, you do not need just one satellite. You need thousands. This has turned into a numbers game that is staggering to comprehend. Before 2019, humanity had launched roughly 9,000 objects into space in total since Sputnik in 1957. In just the short time between 2024 and 2025, SpaceX alone has launched over 7,000 Starlink satellites. And looking at the future filings with the International Telecommunication Union and the FCC, there are plans for over 100,000 satellites in the coming decade. This is not linear growth, it is an exponential explosion. We are effectively encasing our planet in a shell of moving metal and silicon. And while the engineers looked at latency and bandwidth, they failed to account for one crucial factor: sunlight. In May of 2019, the first train of 60 Starlink satellites was deployed. Amateur astronomers and casual stargazers were stunned to see a bright line of lights traversing the sky. It was a viral sensation on social media, but for the professional astronomical community, it was a wake-up call that rang like a fire alarm. This brings us to the optical threat. Astronomers rely on a technique called long-exposure photography. To see the faint light of a distant galaxy formed shortly after the Big Bang, a telescope must stare at the same spot of sky for minutes or even hours, gathering photons like a bucket gathers rain. When a satellite passes through the field of view of a telescope during a long exposure, it doesn't just appear as a dot. Because the telescope is gathering light over time, that moving satellite draws a bright, solid streak across the image. It is equivalent to someone shining a flashlight into your camera lens while you try to take a photo of a firefly. The damage is often total. The streak is frequently so bright that it saturates the telescope's detector. This creates ghost images and electronic crosstalk that ruins not just the pixels under the streak, but the entire data set. This is most critical during the twilight hours, just after sunset, and just before sunrise. This is when satellites are most visible because they are high enough to catch the sun's rays while the observer on Earth is in darkness. Crucially, this is also the only time astronomers can hunt for near-Earth objects, or NEOs. These are asteroids that orbit between Earth and the Sun. These city-killer asteroids can only be spotted in the twilight glare. A sky crowded with moving bright spots makes spotting these faint, moving rocks significantly harder, potentially blinding our planetary defense systems to incoming threats. The poster child for this conflict is the Vera C. Rubin Observatory in Chile. This massive telescope, set to begin operations soon, is designed to photograph the entire southern sky every 3 nights to unravel the mysteries of dark energy and dark matter. It has an incredibly wide field of view, which makes it particularly vulnerable. Simulations suggest that by 2030, 30 to 40% of all images taken by the Rubin Observatory during twilight could be marred by satellite streaks. The legacy survey of space and time is effectively being vandalized before it even begins. And it is not just Starlink. If Starlink was a concern, Blue Walker 3 was a shock. Launched by AST SpaceMobile, this prototype satellite features a massive 64-square-meter antenna array. When it unfurled in orbit, it became one of the brightest objects in the night sky, outshining 99% of the visible stars. It demonstrated that without regulation, commercial entities could launch objects that rival the brightness of the planets, fundamentally altering the appearance of the constellations themselves. But the threat is not just visible, it is also audible. Radio astronomers listen to the universe. They tune into frequencies so faint that the energy collected by all radio telescopes in history is less than the energy of a falling snowflake. To do this, they build massive dishes in radio quiet zones, remote areas where cell phones and Wi-Fi are banned to prevent interference. But you cannot build a wall high enough to block a satellite flying overhead. These constellations beam internet data down to Earth using specific radio frequencies, but recent studies using the LOFAR telescope in Europe revealed a disturbing finding. Starlink satellites were leaking unintended electromagnetic radiation. Their onboard electronics, power inverters, clocks, and processors were humming with radio noise that drifted into protected astronomy bands. For a radio telescope, a satellite passing overhead leaking this noise is like a roaring jet engine flying over a library. It deafens the sensitive instruments. As these constellations grow, the concept of a radio quiet zone will become extinct. The search for the faint whisper of hydrogen from the early universe, or the techno-signatures of extraterrestrial civilizations known as SETI, could be drowned out by the noise of our own internet usage. We must also acknowledge that the loss of the night sky is not just a scientific loss, it is a cultural theft. For millennia, the sky has been the canvas for human mythology, navigation, and timekeeping. For indigenous peoples, the sky is often as important as the land. The Aboriginal Australians, for example, look for the emu in the sky, a constellation defined not by bright stars, but by the dark clouds of dust within the Milky Way. When thousands of satellites illuminate the background sky, a phenomenon known as orbital skyglow, the contrast needed to see these dark constellations vanishes. Critics have termed this astrocolonialism. Just as colonial powers once claimed indigenous lands without consent, private corporations and a few wealthy nations are now claiming the sky. They are unilaterally altering a global commons, the view of the universe that belongs to every human being, for the benefit of subscribers in the Northern Hemisphere. A child born in the Andes or the outback in 2030 may never see a pristine night sky, their view forever scarred by a grid of moving artificial lights. Beyond the loss of science and culture, there is a physical danger looming over us. The sheer density of traffic in low Earth orbit is creating a minefield. In 1978, NASA scientist Donald Kessler proposed a terrifying scenario. He theorized that if the density of objects in orbit gets high enough, a single collision between 2 satellites could generate thousands of pieces of debris. Those pieces would then smash into other satellites, creating a cascading chain reaction of destruction. This is known as the Kessler Syndrome. We are already seeing the warning signs. Automated collision avoidance systems on Starlink satellites are now triggered thousands of times a day. They are continuously dodging debris and other satellites in a chaotic orbital dance. We saw a glimpse of the danger in 2021, when Russia destroyed one of its own satellites in a missile test, creating a cloud of debris that forced astronauts on the International Space Station to shelter in their escape pods. A full-blown Kessler event would turn LEO into a shredding machine. It would destroy our GPS, our weather forecasting, and our telecommunications infrastructure. Worse, the debris belt would act as a barrier, making it too dangerous to launch rockets through it. We would be trapped on Earth, imprisoned by a cage of our own junk. Furthermore, there is a second, often overlooked environmental threat. LEO satellites are designed to be disposable. They burn up in the atmosphere after about 5 years. But they don't just disappear. They vaporize into aluminum oxide and other chemical particulates. Scientists warn that depositing tons of aluminum into the upper atmosphere could trigger unpredictable geoengineering effects, potentially damaging the ozone layer or altering the Earth's albedo and climate. So is the situation hopeless? Not necessarily. The astronomical community, rather than just protesting, has moved to diplomacy and engineering. Following the outcry over the first Starlink launch, SpaceX began working with astronomers. They developed DarkSat, which used dark coatings, and VisirSat, which used sunshades to block sunlight from reflecting off the antennas. While these measures helped reduce brightness, they didn't solve the problem entirely. Visors interfered with laser links, and the sheer number of satellites still creates a collective glow. However, it proved that the industry can adapt if pressured. Astronomers are also developing AI algorithms to clean images, identifying and subtracting satellite streaks. This works for bright streaks, but it introduces noise and cannot recover the data hidden behind the streak. It is a band-aid, not a cure. The root of the problem is legal. The Outer Space Treaty of 1967 was written when only 2 nations could launch rockets. It did not anticipate mega-constellations. Currently, the Federal Communications Commission in the US grants licenses based on radio interference, not light pollution. There are no binding international laws that limit how bright a satellite can be. The International Astronomical Union has established the Center for the Protection of the Dark and Quiet Sky from Satellite Constellation Interference. They are lobbying the UN to treat the dark sky as a protected environment, much like Antarctica or the high seas. They argue for space traffic management, a global air traffic control for orbit. We stand at a crossroads. On one path lies a hyper-connected world, where high-speed internet is a universal utility, democratizing information and education. On the other path lies the preservation of our cosmic heritage, the ability to look up and see the universe as it truly is, and the ability of science to warn us of threats and answer the deepest questions of our existence. It is a false dichotomy to say we must choose one. We can have internet and astronomy, but only if we abandon the Wild West mentality of the current space race. We need strict limits on satellite brightness. We need mandatory debris removal plans. We need to reserve orbital shells for science. And we need to recognize that the sky is not a resource to be mined by the first company to get there, but a global commons that belongs to us all. If we fail to act, the next generation will not look up and wonder at the stars. They will look up and see only a mirror of ourselves, a ceiling of moving lights shutting us in, alone in the dark. Thanks for listening to G Fun Facts Online.